friends, now come out of the classroom. It's enough. We have seen lot many algebraic expression, lot many mathematics. I'm afraid that we should not get lost, and we should not forget that finally we have to build a relationship with an aircraft. So let us try to understand whatever we have been writing on the blackboard, what exactly we are doing. Remember, when we are writing equation of motion, the thrust equal to drag, lift equal to weight, we have given a statement that we are assuming it to be point mass model, right? What is that? Point mass model physically means, let us see, this is our Hansa 3 aircraft. I always say this is pride of India, in particular NAL, Bangalore. They have manufactured it, designed it. Now let us see what is the meaning of point mass model. If I ask you a question, where is the CG of this airplane? How can you guess? One first sight common sense tells the CG should be somewhere near the landing gear, this landing gear. But the next question is whether the CG will be ahead of landing gear or behind landing gear. Now if you think carefully, if the CG was behind the landing gear, then if there was a slight disturbance in the tail, the airplane will hit the ground, even while on the ground, right? So you will not like to keep the CG behind the landing gear, although CG will be close to landing gear. That is why if you see an aircraft, the landing gear, once it's located, you know CG will be somewhere very close to landing gear, but ahead of landing gear. So we say the CG is somewhere here. And second part, how do I distribute the mass so that CG is at a point where I want? One is okay, I have seen the landing gear, so I'll put it little ahead of landing gear. Second thing you see here, this is the thrust line, okay? And if the vertical CG is very away, very far away from the thrust line, then this thrust will be giving a moment about CG, and the pilot will have to make some corrections before he goes for a flight. So natural tendency would be try to keep the CG in the central line. But it may not be possible all the time, because sometimes wing is a low wing like here, sometimes wing could be a high wing. So you try to ensure that the CG in the vertical side, vertical height is close to the central line. But what we are now talking about, once we have identified where is the CG, then I will try to take the advantage of Newton's law of motion. If you recall F equal to ma, for a distributed mass, I can show that F equal to mass into acceleration of the center of mass. That is, if there are different particles and the force is acting on each particle, then if I want to measure the acceleration, predict the acceleration, I can easily do that prediction if I assume that all the masses are at center of mass, and that acceleration will be the acceleration of the center of mass. For our case, center of gravity and center of mass is the same, right? That is what exactly the point mass model will be doing. That assume that no more mass is distributed, because we are only interested in the acceleration for rectilinear motion. We are not talking about rotational motion. If rotational motion is there, then I am more bothered about moment of inertia, because distributed of mass, that is important. When I am talking about acceleration for rectilinear motion, I am interested in the acceleration of the center of mass. So it is fair that I assume the whole mass is concentrated at the center of gravity. Okay? Now, once this is done, that center of mass I have identified, and I have agreed that I will be applying F equal to ma to analyze rectilinear motion. So what are the forces? Now let us also have a closer look. If I separate out fuselage, wing, tail, and other components, I can fairly do an approximation. Let us say the forces on the fuselage is acting somewhere here. Okay? That is the lift. I am talking about the lift part. Similar drag will be acting like this, depending upon velocity direction. Do not forget, lift will be perpendicular to the velocity and drag will be opposing the velocity. Okay? Let us take example of a lift. For a small angle of attack, if this is the lift direction, but I am writing equation of motion assuming the whole mass is at center of gravity somewhere here, so then I need to transfer this force from here to the center of gravity. And once I transfer a force from here to a distance, I know that I can transfer this with the force as well as the moment. Okay? So I am putting, because of this fuselage, there is one force, which is lift and a moment. Similarly, take case of a wing. So there will be a force, lift force. I again transfer it with a moment to the CG. Similarly, from the horizontal tail, all those forces which were acting at different point of location, I am transferring them to CG with force and moment. So now, when I apply point mass model, I have an assumption that all these moments are balanced. And in practice, how they are balanced? They are balanced by design, by a configuration design. And in addition, you can use elevator, trimmer, etc., to make all those things moments are balanced. So now, when I am analyzing the cruise, I am very clear that whole mass of the aircraft is a center of gravity, and net force I have calculated by transferring them from different components, and then I am now resolving those forces and finding accelerations, and if it is a non-accelerated or unaccelerated flight, I am putting that 0 and going step by step whatever is required, right? So that is what is typically the point mass model. But when I say this typically, when I am talking about forces separately on fuselage, on wing, on horizontal tail, and going and trying to add them with a lot of care that I know there is an interference effect, right? This method is called component build-up method. That is, you find out the component and then add. But in actual practice, what will happen, you will like to find the overall pressure distribution over the whole airplane, and then find out the resultant forces, and find out where they are actually acting, and then try to transfer them to CG. Typically, we use CFD, computational fluid dynamics, or second stage, what we do, we try to go for a wind tunnel testing and find out the pressure distribution or find the forces acting through the balances. There is a balance which will measure forces and moment. Okay, that is a matter of detail. This is the basic background when we are talking about equation of motion and point mass model. Right? Before I stop discussion on this, please also understand we have also shown you that over the wing, if I try to represent where should the lift will act or CL will act, then I know that it should be at the quarter chord point. That is, I take this chord and act 25% from leading edge. So I'll say this is my CL, location is here. Okay? So these are the things which need to be kept in mind. So similar thing will happen on the other side, and we will define something called mean aerodynamic chord. You will see as we develop this course. But at this point, it is important to understand what is the meaning of point mass model, and how the forces are transferred, and what is the effect of that. Okay, up to this point, this is fine. But let us go back to George Calais. When George Calais told us that yes, and he was pioneer in making us understand that if there is an angle between the plate and the velocity vector, there will be lift. There is a plate and there is a velocity vector, there is a reaction, and component of that is lift, one is drag. This is fine. But when you try to go deep into it, how this lift depends on the environment or the geometric dimensions of the wing or the flat surface, then we have to understand few things little more deeper. Let us see what happens if a flow is passing over this wing surface. Because air has viscosity, so what will happen? The layer, the particles which are just on the surface, they will get stuck to this surface because of property of viscosity. That means they will not have any motion. They will have the motion of the aircraft. They are now part of the aircraft. So relative sense, they have no motion with the aircraft. However, as I go higher and higher, the influence of this viscosity via the wing surface gets diminished. So at some point, it regains its, let's say, regains its velocity. So that boundary layer thickness could be, it's not a huge boundary layer for the wing, but it depends upon something which I call Reynolds number. That is, please understand, when a fluid is flowing over this, it has a inertia, right? It is, I'll use, it has a inertia associated with the momentum of the fluid, right? In textbook, they call it inertia force. So that will try to ensure that it remained in the state of motion. However, because of viscosity, it will try to drag it, try to discourage that motion. So now, who will dominate? That will be decided by the ratio of inertia force and the viscous force. And ratio of inertia force and viscous force is only defined as Reynolds number. So we say if Reynolds number is high, that means relative sense the inertia force is more than viscous force. So the flow, the pressure distribution over it is less influenced by the viscous effect. But if the flow is low Reynolds number, then you say the viscous force is more dominating the inertia force. The pressure distribution and other characteristics are dictated by primarily by the viscous effect, right? So whether it is high or low, one thing we agree that the lift part has some implicit relationship with Reynolds number. Drag has some relationship with Reynolds number. What is that Reynolds number? How do I use that? Those are questions were answered through dimensional analysis. Okay? That is why we did dimensional analysis in last class. So what we will be doing today, once we understand this, we will again revisit the dimensional analysis, which is typically pi theorem, Birkingham pi theorem, very important, very, very important theorem, which is used many designs. Okay? So let us now from here go back to the classroom and we continue. We have just again came back to the classroom after seeing our Hansa 3 aircraft and try to correlate what we are teaching in the classroom to what actually happens in the aircraft, right? Let us see, we again go back to George Calais. Why we are again and again going to George Calais? Try to understand that, okay? Remember, this was contribution of George Calais that there will be reaction. By now, you are very clear. The flat plate moving like this, there is a reaction, and one component is lift, one component is drag. Absolutely fine. So one thing is very clear, this lift will be proportional to the angle alpha, right? It will be proportional to ADIS. It will be proportional to velocity, density, then shape, then maybe viscosity, and I am also writing something compressibility, because air is compressible. If the vehicle moves a little faster, then the air particle get compressed, and accordingly we have defined three types of flow. Remember, or you can check, if it is less than one, we call subsonic flow. And what was Mach number? Mach number was velocity of vehicle, or speed of vehicle is more important. It doesn't matter for rectilinear flight, by speed of sound. Right? Why this was important? Conceptual wise, I know that disturbance propagates with the speed equal to velocity of sound, or called speed of sound. So suppose that the vehicle is moving like this, then the air particle get disturbed. So any air particle ahead of the vehicle is already displaced because of disturbance. So when it moves, it gets less resistance. But imagine if it is moving with speed higher than the speed of sound, then the next particle, before they get displaced, the vehicle will crash on it. That is how the fluid particle gets compressed, and we call it's a supersonic flow. That is Mach greater than 1, which is supersonic. And there we have shock waves. Right. Shock waves are like, this is the vehicle moving in this direction, so fluid gets compressed, and there are shock waves, high density. They get compressed like this, so the shock wave is formed. This is not part of this lecture, but you need to know a few things, to make your understanding better. It goes without saying, if Mach number equal to 1, it is transonic. Okay? And we are talking about incompressible flow when, that means we are talking about typically Mach number less than 0.3. Most of our lecture is governed by this condition. The Mach number is less than 0.3. So keep that back of your mind. Now see here, if the lift is function of alpha, area, velocities or speed, density, shape means, by now, aerofoil, what type of aerofoil, what is the contour of the aerofoil, right? Then viscosity and compressibility. Okay. Now imagine if I want to create a database where I need to know what is the lift for given area S. What I have to do? I have to go to a wind tunnel and I will conduct a test, put that wing, conduct a test, and keep alpha, V, rho, all these things same, but I'll go on changing S. Correct? Similarly, if you want to know what is the effect with V, I will keep other variables same and go on changing speed inside the tunnel. Like that, I'll be doing similar thing for all the parameters. So it becomes a Herculean task, right? Very difficult to scale it up, okay, or scale it down. That is, I am very much restricted by the amount of testing required to really capture the model. That is where the use of dimensional analysis helped. This is typically using Buckingham pi theorem, right? If you get a chance, go do internet surfing and read something more about it. In that, what we did, we said, let us identify lift as function of, let's say, V, rho, S, A, and mu. Mu is the coefficient of viscosity. That is, we are trying to address a question. It is fine, lift is proportional to angle of attack, fine. But at a given angle of attack, it is also function of so many other things. That model I am trying to capture, okay? In doing that, we use the benefit of dimensional analysis. What we did, we know the dimension of lift, dimension of speed, density, area, etc., and we compare them. Before doing that, we wrote L equal to Z, V to the power A, rho to the power B, S to the power D, A to the power E, and mu to the power F. This exponent, A, B, D, E, F, they are all constants. Z is also a constant. Then what we did, we compare the dimension of left-hand side and dimension of right-hand side. Form some equation to get finally very important result. As lift equal to Z rho V square S A by V to the power E and mu by rho V S to the power half to the power F. And we identified that mu by rho V S to the power half is 1 by Reynolds number, and Reynolds number we know that it is ratio of inertia to viscous force. And that is, one can show the derivation rho u L by mu. L is the characteristic length. If you see here, this is rho u, u is the velocity here, that is the same v here, and s to the power half has a unit of length. So this is L is here. Okay? And mu is the coefficient of viscosity for air. Correct? Also we identified here A by V is 1 by Mach number. So message here is there are two non-dimensional numbers which are to be used to reduce your number of testing and adding better values in the interpretation of whole of this modeling. That is, when I talk about this as a Reynolds number, I understand this is inertia to viscous force. When I talk about A by V, I understand it is with the Mach number. So we now express this as half rho V square CL, where CL is, where CL by 2 we have written as Z, 1 by M to the power E, and 1 by RE to the power F. By doing that, what has happened, you see? Now we know the CL is function of alpha we are knowing, also Reynolds number and Mach number. Our life has become so simple. How do I utilize this? Question is this. And what is the CL? CL is the coefficient, okay, lift coefficient here. My question is, do I work with L or I work with CL? What is the advantage I get? If I try to give a physical interpretation to this, it says, if I am having two geometrically similar configurations, right? Geometrically similar, you understand, their lengths are proportional, right? If you have a geometrically similar configuration, then to know the variation of CL with alpha, Reynolds number and Mach number, I need to do very limited number of experiments and be careful. First identify what is the speed regime and which one is important, Reynolds number or Mach number. As we are doing here, for Mach number less than 0.3, it is incompressible. So if I want to model CL, I will not give weightage to this. I will know that CL will be function of alpha, yes, and Reynolds number. That is important, right? So what I do, I suppose there is a big airplane, okay, and this is flying at, let's say, 90 meters per second, so less than 0.3 Mach number. Altitude is chosen like that. Now, what do I do to take help of it? I make a smaller, similar configuration, exactly geometrically similar. Okay? We call it scaled down model. Maybe 1/25th, 1 by 50th, 1 by 10th. Each dimensions are reduced like that. Then I put this inside this tunnel. I want to generate CL versus function of alpha. So what I can do now? I can go on generating different CL by giving different orientation and ensuring one thing that is very important. When it was flying at a particular altitude, okay, what was the Reynolds number it was flying? So I calculate rho u L by mu. L in this case will be the chord of the wing. So I know what is the Reynolds number the aircraft was flying. I will duplicate the same Reynolds number here, because here I know Reynolds number again is rho ul by mu, where L will be the chord of this scaled down model. If I can ensure that this flow has got such a speed density combination that Reynolds number experienced by this body is exactly same as what is the actual airplane was seeing, then if I model CL, I can generate CL as function of different Reynolds number. Okay? And depending upon what altitude the airplane is flying, I can use that CL value for actual computation. However, when I do internal testing, there are some limitations. There are some error introduced because of wall effect, because of the model may not be exactly the same, but those are secondary things. Physics is this. If you can do that, then I am saving so much of testing and my life becomes simpler. And this is the concept that if you have a geometrically similar, that is geometric similarity, and the flow dynamic similarity. That is, I am duplicating the Reynolds number. Okay, so that makes our life very simple. So we'll stop it here with a final statement. Through this pi theorem or dimension analysis, I now know that CL not only is modeled in terms of alpha, but Reynolds number and Mach number. So our approach will be, first I'll use it. Now from here I'll go to aerofoil. Okay, then aerofoil to wing, and wing to flying.